Morning, everyone, or evening, wherever you are in the world. My name is Ellie Sansom, and I'm a researcher at Curtin University's Space Science and Technology Centre in Perth, Western Australia. I'm a planetary scientist.
My name is Christopher Moore. I work at the Harvard-Smithsonian Center for Astrophysics. My research focuses on solar physics and space-based instrumentation. And we'd like to welcome you all today for the International Astronomical Union Early Career Astronomers Discourse Series. Today, for the 10th version, we have Dr. Richard Scalzo. Richard is a senior research scientist at the University of Sydney, Node of Data Analytics for Resources and the Environment, DAR, an ARC Center and PhD training program in data science to solve Australia's environmental challenges across mineral exploration, ground and surface water, and biodiversity. He received his PhD in physics from the University of Chicago in 2004 and held postdoctoral positions at LBL, Yale, and ANU, leading work in time domain astrophysical surveys before switching to data science in 2015. Dr. Scalzo's current research involves advanced data fusion and Markov chain Monte Carlo methods for environmental science problems, with current emphasis on 3D modeling for geology and geophysics. He also has independent consulting experience in short projects across water, forestry, and green energy.
So this is going to be a 30-minute talk by Richard. I'm really excited. And then we will have a 30-minute discussion session at the end. So if you have any questions, keep them out and start posting them in the Q&A feature in Zoom, or you can chat on YouTube and we'll be monitoring those as well. If we do run out of time, we'll take note of all the remaining questions and ask them at the and try to answer them in writing afterwards. So take it away, Richard.
Right. Yeah. Thank you, Ellie. Thank you, Chris, for inviting me. It's a real pleasure to be here. I have so much to tell you. I'm positive that I have prepared too many slides, but it's going to be a challenge to compress it all down. But I'll do the best I can. If I don't get to the thing you were wondering about, please ask a question in the chat. Or if you don't get to it during the hour, then find me. I'm at Scalzo Nova on Twitter. So. I hope to hear from you soon. So a quick, I guess, you tell them what you're going to tell them, and then you tell them, and then you tell them what you told them. So here, what I'm going to tell you is something about something about how I got to where I am right now, I guess, because it's maybe helpful to have some context for that. Then tell you a bit about the DARE Center that I'm involved with in its complex model view of data science. Talk a bit about quantifying uncertainty, some of the tools we use to do it. And then a few examples, if I've got time, from our ongoing work here. Any of these subjects could probably be its own talk. So I'm really, as I said, very happy to go into more detail offline if you ask. As we've said, I have a history going back some years. I did my PhD in Chicago in gamma ray astronomy, and then held various postdocs at Lawrence Berkeley Lab, Yale University, and ANU, working on type 1a supernova surveys. So that gave me two kinds of experience that I think are relevant for things I did later. One is the big data side, which is represented on the left by my work on software pipelines for discovering supernovae. In particular, the image template subtraction that you use to discover supernova on top of static galaxies. So you would subtract a reference without supernova, then you'll see a supernova appear as a nice point source that you can just detect and do photometry on. So we had the robotic telescope called SkyMapper. That's my most recent iteration of this. I've done others though. My work on SkyMapper was for Brian Schmidt at ANU. There was some machine learning involved in that in the classic, I guess, big data sense. Not many training examples because supernova are hard to find, but we did eventually bootstrap it up to the point where we could reliably tell a good supernova candidate from the artifacts or junk that might appear in those images. And the other half of it is the complex model side, where having found the supernova and having gotten light curves from them, you want to tell something about, about the physics of the supernova, how it exploded. And so I ran a piece of Bayesian inference to infer the ejected mass from samples of type 1a supernovas. So this is the most recent version of this diagram. I have a series of papers talking about this, where I guess the classic picture was that type 1a supernova would blow up at the Chandrasekhar mass, but what I've actually latched onto through this modeling is that they come in a range of masses, and moreover that the explosion mass is actually related to the light curve width that you use to standardize them for doing cosmology, if anyone is familiar with those measurements for the accelerating universe. So that was, I thought, a really interesting discovery that hinged on being able to make inference with very limited data. So something about 5 or 6 years ago, I applied. I was on the job market. I applied to a range of continuing positions, but wasn't getting much traction. And it's been 10 years since I got my PhD. So I figured I could keep trying to do this, or I could try to do something else. So data science was the hot thing at the time. It was a popular pivot for astronomers to do something else, and they had boot camps to retrain you. But the usual corporate data science stream didn't quite feel right for me. So I thought long and hard. I talked to all my friends, and decided in the end to look for something sort of more of a consulting style role where I get to work on a lot of different problems and work with a range of different people on different kinds of things to get a taste for what kinds of things I might want to do later on. And also in particular, if you're engaging with all those people and you're leading those projects, then that hones leadership skills I could then hopefully use to leapfrog to some other more senior position, as opposed to starting on the bottom rung in an entry-level data science position. So something from my 10 years of experience, I guess. So that's what I was looking for. So to go into more detail on the flip side of these things, when I think of, and this is something of an overgeneralization that there is bleed over between the two, but the overall ethos of data science, I guess, as a popular term, is associated with the big data stream. Big data in the cloud computing and so on. So the fields of science, I guess, you'll most commonly find associated with this are particle physics, which have big experiments with huge amounts of data taken to find rare particles. Astronomy, of course, with its large general purpose surveys. Molecular biology says it's big data, and it does take a lot of storage to store the data. It's probably more accurate to say it's high dimensional data because the sample size is often not that big. In industry, you'll have retail and finance, industrial processing that are taking many records a minute. So you're trying to, overall, you're focused on prediction. You're focused on extracting features from the data that will allow you to make predictions. And you're making many smaller reversible decisions at scale. So you're automating repetitive tasks. So common questions, I guess you might ask in a particle physics experiment, you want to know if this detector event is junk or not. If you're classifying images, you want to be able to find which ones are of cats and which ones are of dogs. If you're doing high-speed trading, when in the next 200 milliseconds should I make this trade? You might, there's applications in ad service and customer retention and so on. So things like that are common applications. There are areas though where even big data are not actually enough data to help you constrain your problem. So, those fields of science are going to be, I guess, what we would call the narrative sciences. There's some physical science elements as well. So geology, hydrology, ecology, weather and climate. So these are systems that involve many complex interacting parts or histories that seem arbitrary from our point of view, but we believe are as a result of processes in nature. So in industry, these come up under resource extraction. So if you're a mining company, you want to find the next big ore body, then you have to know the processes that formed that. You have to know something of the terrain you're looking in, what the signs are, with enough confidence that you're willing to shell out money to sink drill holes into the ground, for example. Same kinds of things show up in insurance, if you're looking at rare events, you're not interested so much in the bulk, but you're interested in those few things where the data you have to constrain those events are not voluminous at all. In fact, in consulting, where you may be called upon to have to work on a range of problems that aren't sort of cookie cutter problems that show up again and again in different businesses. So these are focused on causal inference and quantification of uncertainty. So they're good for not for minor decisions so much, where you can sort of make up the ground if you make a mistake, but you have but major irreversible decisions that are often made with sparse or unreliable data. So you're providing decision support for humans. So like things like, should we build a new desalination plant for our city in the next 20 years? You know, how much fishing is too much fishing? How big a storm does this infrastructure need to withstand? And that's particularly important under climate change, where the conditions that you have, you need a model that can generalize well out of its training set, because the conditions we're going to have in the future are not going to be the same kinds of conditions that we had in the past. And so training a model on past weather conditions or climate conditions is not going to help you. So I guess I first got involved in this complex model kind of line of work, which is the direction I ended up going in when the University of Sydney started its Center for Translational Data Science in 2015. So I applied for a job and got it. That was an investment by the University of Sydney in data science, and along the lines of similar centers you'd find at University of Washington, UC Berkeley, NYU, where the university is making an investment in data science as opposed to having a grant-funded center. So this was under the Faculty of Engineering. It was focusing on real-world grant challenge problems that we could use that were so hard that you needed to demonstrate new data science methods in order to solve them. In particular, for a Center of Excellence bit, a big grant that we put up, here are some examples of how those verticals, the geology, human metabolism, and criminology, would interact with the method-oriented subfields of study, understanding the scientific method and exploring and explaining models, linking and managing data. So what we would call the domain problems go along the verticals, the data science problems go along the horizontals, and they cross-pollinate each other. So for us, this meant mostly not the big data side, but the complex model side, trying to find problems where you need to incorporate some expert knowledge about the structure of the problem into your model structure. So the role I had within CTDS was to come up to speed very quickly in new areas and kickstart new collaborations to support large multi-million-dollar grants that we were going for in order to continue to support the center beyond the university's seed funding. So we worked. So I worked on a bunch of things: molecular biology, public health. So here's a map down here in air quality, where we're trying to map air quality with drones. That's the dotted line or the dashed line. And geology, which is to say 3D modeling of structural geological or varying systems, mineral systems. So that so the thing you see on the right-hand side is a cutaway 3D view of one of my models. Probably the most important thing I learned in the process is that cultural intelligence is important even among scientists, even apart from industry or government or interacting with other sectors. Just understanding what other scientists are doing can be difficult, because they'll have not only different jargon but actually different approaches to thinking about science, different incentives or publication requirements or things like that. So eventually we were successful in getting one of these grants up. This was with a bunch of our data science collaborators on the side. So I'd like to thank them all for supporting me on my own work. So the director, Sally Cripps, is up at upper left, along with our colleagues at University of Sydney, University of Western Australia, UNSW. In the middle row, we have our domain collaborators among problems in water, mineral exploration, biodiversity. Then the research fellows are over on the left-hand side. I've got a background in physics. Nandini has a background in climate science, and the rest of us are the rest of the research fellows are mostly machine learners or statisticians. So what makes DARE different is that this time around, the domain problems are linked. So it would be hard for us to say, I guess, what geology and criminology had in common. But in this case, the actual decisions you're trying to make are linked across the verticals. So in the center of this diagram, you'll see this same matrix structure. Minerals, water, and biodiversity are the three verticals, and the horizontals are exploring data, building models with this data, and then actually using them to make decisions. But the domain problems are linked across those verticals. You've got, if you're trying to operate a mine, that'll have impact on the water use, which will have impact on the biodiversity in the area, for example, and also on the town next door, where they were concerned about their water supply and water quality. And so understanding how those needs interact is important, and modeling can help you do that. The geology and the hydrology come together in trying to model groundwater. You're trying to understand how water collects in rocks and flows between them. Hydrologic responses to climate change are, as I said, important because the underlying conditions will be changing over time. Forestry and soil are also involved in this. So we'll be training PhDs in data science techniques. They'll be embedded in partner organizations while we're doing this, but we'll be still doing maths research. So the grant then becomes sort of a focal point for getting ongoing support from industry or government. So if we want to write a new grant or to approach a new partner to buy into the center, we can do that and sort of sustain ourselves as time goes on. So this is the nominal length of the grant is until 2023 or 2024, but we hope to continue going after that and have a whole theme of data science for natural systems. So my role is the DARE Project Science for Geology. I'm becoming increasingly involved in hydrology lately. So what this means is that I work with the partners and the other domain scientists to translate their interesting problems, which if we solved them would totally transform their domain into high impact data science research. So that means I do partner engagement, I do grant writing, definitely helped assemble many of the grants that are keeping us going here. Supervision of junior scientists. I do a bit of teaching because it's a PhD program, so we have courses, and everybody's got to pitch in the teaching a little bit. And of course, research on probabilistic models. So this kind of thing is the kind of thing that I find often in these problems where we're looking for where the resources are. How do you extract them sort of at minimal cost and with minimal disturbance to the surrounding environment? This process is expensive. So if we were able to use non-invasive methods, data taken at the surface or a select number of boreholes into the ground, we'd be able to locate those resources quickly and develop them easily. We'd also eventually, in the costs nominally are labor and parts and so on for drilling holes, but we'd like to include the cost of cleaning up mining tailings or things like that. Ultimately, in our modeling, that may be among the things that we end up working on. This talk was the headline of this talk was quantifying uncertainty, and I haven't said a whole lot about that yet. So I guess I'll go through what I mean by uncertainty. And so these, in physics, I guess we're used to thinking about it in terms of error bars or sometimes parameter uncertainty, but it can be any uncertain factor that influences a model. So that might include sparse and or unreliable data. If you've got big gaps in your data, you probably have to interpolate over them. So here's an example from my supernova work where this is actually pretty good looking data, but there were some pretty ratty light curves that I saw where I'd need complete wavelength coverage at a dense series of time points. And so you've got to fill in the holes, and you need to do that with respect to every time you fill in a hole with interpolation, you're reusing information. So being sensitive to that. This might be drill holes, say, if you're working on a geoscience problem. The measurements may be indirect. So you've got photometry, which is integration over some series of wavelengths, but that in itself came from some physical process. And if you're trying to infer something about the physical process, then actually modeling the whole thing end to end can help you get a handle on that. But that means that the analysis won't be simple. It means that you need to actually model those processes and the random elements of them. So there's the general parameter non-uniqueness. This is an example of, from my supernova work, of the ejected mass versus the nickel mass, both of which are physical quantities we were interested in for 1A supernovae. You can see that there's a pretty broad area. They're correlated. There's not a single answer. There's a distribution of answers. And so actually capturing that parameter uncertainty is critical for interpreting what we're doing. There may be nuisance parameters you don't care about at all, but they affect the answer. So there may be the ways the nickel is distributed in the supernova, or how the it's like how the radiation is trapped within the supernova. And so in this case, I don't actually care about those results, but I've got to incorporate them anyway. And instead of trying to optimize, I'll just I'll just integrate those out. I'll just average over all possible values, and then that means that my error circles blow up in for the other parameters, but at least I've incorporated that uncertainty. The model may be misspecified. If you're working from a template, the template may diverge from the observations. So you need elements in your model to account for that. You may need to select between completely different sets of models. So the whole goal of that research was to determine which progenitor channel the supernova came from, and they all had different mass scales. But you can think of that as a form of model selection. In other cases, it may be like, is there an ore body here or not? Is there an aquifer there or not? If there is an aquifer, is there a path for water to flow from point A to point B? Those are things that may be completely different models that you then need to compare. The story of all this, I guess, is that we use Bayesian methods mostly to do our work. And Bayesian methods form a rigorous, mathematically coherent way to look at all of these issues quantitatively. If you talk to some people, they'll say that this is the only way to do it in a self-consistent fashion. So if you haven't worked with Bayesian techniques before, because it's hard to work in astronomy these days without running into them. In the broader parlance, we'll call it explainable AI, just to give it that much more cachet. But you'll have a probability distribution that shows you the range of answers in your problem solution. You'll have prior beliefs or expert knowledge, which are the starology things, the geology, the hydrology, that'll be your input on, and they may take the form of distributions in your model parameters, which are the thetas, or the constraints on the model, which are also the thetas, but maybe more complex than just, say, a range of parameter values. And you'll have a likelihood, which is the star physics, the geophysics, the astrophysics, that tell you, sort of given the parameter values and their likely interrelations, how do you go from that to generating the data that you saw? And so you put the prior and the likely together, and you'll have something proportional to the posterior. So this combines all the information in a principled way. You can update beliefs as new data become available. You can quantify the uncertainty by sampling parameter values that represent different states that the model could have. And you can use that then to make different decisions as well, not just in an inference context, but also in a prediction context, because different models with different parameters give different answers. And so, you want to, if you've made inference and you've quantified parameter uncertainty, you want to push that forward onto your predictions as well. So the main tool we use to do this is Markov chain Monte Carlo, which is also, I think, more and more commonly used in astronomy these days. But it's a way of drawing parameter values given your posterior, given a probability distribution. So you start from some set of parameters, you'll propose a new state. Based on the previous state, you'll have some probability density that you use to do that. You'll generate a random number between 0 and 1. And if it's less than this quantity that is related to the ratio of posterior densities between the point you're at and the point you're going to, but also to the proposal densities. If you get this random number less than alpha, you accept the new state, you move on. Otherwise, you reject it. You add a copy of the same thing to your chain, which is important. If you don't do that, you'll get the wrong distribution. So this is the Metropolis Hastings algorithm. it's commonly used for doing model inference. Over time, the values from this chain are distributed as the posterior. So, okay, that is actually much of our research because the proposal that you use makes a difference. In this case, I've shown two-dimensional cross sections of, well, this is actually contours from a two-dimensional Gaussian, and I've got three competing proposals here. I've got an isotropic random walk, an anisotropic random walk, and then a third random walk that's actually optimized for infinite dimensional problems. And you see they mostly do, they do all right. They all cover that Gaussian. If I then go to 100 dimensions, the regular random walk that is the classic one that you normally use doesn't go anywhere at all. It utterly fails to sample things. The random walk that is adjusted and tuned so that the steps it takes are preferentially along that long axis does reasonably well. But only this third version of the random walk that's related to infinite dimensional problems, actually from drawing random functions, is able to navigate that. So the proposal you choose matters. Here's some worst case posteriors. They're pretty terrible, where you actually have this is a case where we're trying to do inference on surface processes of erosion and of a landscape on the coast of Australia. And so we're trying to understand the rainfall and the susceptibility to erosion of the land in this area in this paper. The posterior that we got from just scanning across it, not even from sampling, is shown on the right. And you can see it's multimodal, it's spiky like a hedgehog. So we need to be able to come up with proposals that are able to cope with that sort of thing. This is something I probably can't resist going into, even though I probably should. So many proposals were invented by physicists, and they're actually informed by physical processes. So if you've studied physics, you'll have a heads up on that. I've kind of dunked on Metropolis random walk above, but it's really just the first go-to proposal. If you can do better, you may have heard of Hamiltonian Monte Carlo if you've done anything with the STAN package, where you treat the current position of the chain as a particle in a potential. Where the potential is actually related to your posterior density. And so if you can conserve energy for this particle by integrating in classical mechanics trajectory, you conserve probability as well. And so your proposals can move very far from the origin and be accepted almost all the time. There's another type I've encountered, which I was unaware you could do, where you can actually jump between chain states that have different numbers of parameters or parameter spaces with different dimensions. So suppose you've got something like this, which is just a stepwise function, but you don't know how many steps it has. You're trying to do regression with that kind of a model. That gives you chain states, that allows you to actually average over the number of line segments in this model. So that has applications in all kinds of places, but it was something that is kind of bent my head when I saw it. You can do one better on Hamiltonian Monte Carlo and actually use the higher order derivatives of your probability distribution. You get something that looks a lot like general relativity on probability distributions, which blew my mind. So in this way, you get something that's perfectly tuned all the time and moves exactly as much as you expect to get a reasonable change in the parameters, the probability density for a change in parameters. And there are options as well for multimodal distributions where you can hop between modes, but still come out to the right mixture of probability between modes. So I realize I'm running short on time, so I'll try to just zip through a couple of examples. Most of the problems I work on are inverse problems where you have you might have a world that's parameterized in terms of rock properties, say. So in this case, for geophysics inversion, it might be the rock density for gravity. The rocks will show you gravity at the top, at the surface, but there'll be some stuff underneath, for example. So you'll parameterize it by that density as a random field, or if you have some parametric idea of how it should vary across your volume, then you can just build that in. You'll have sensor data that is a transformed version of that, and the inversion comes from adjusting the parameter to fit that and to generate an ensemble of possible rock densities under the ground. This is only in one dimension, but you can use it in 2 or 3 dimensions. And that's actually what I will do next. So quick concrete examples. You can use this there's a recent paper we had that's just been submitted where we're trying to understand, we're trying to do inventory on water resources using remote sensing. So this will be a situation where you've got some varying height of water in a reservoir, and if you have a gauge to measure that, and you have the profile of the reservoir, then you can just integrate it. You can see the water goes up and down. It has a different footprint over the top. If you don't have a water gauge, that's what you'll need to use, a detector that's sensitive to water. So the world parameterization is just that water level. You'll have a forward model in this case, which will be the process of integrating that reservoir through a series of vertical profiles and seeing how the footprint changes. You can then model every pixel just as you would in an astronomical image. You even have to worry about the registration. That was actually one of the left and right, up and down registration was a big problem for us until we realized that we needed to add that parameter because the images weren't perfectly registered. So we put priors on all the parameters. We use that to back out water volumes based on those overhead areas. And so you can do, then you can use this, but you can do it at scale and use this for water accounting and for regulating water use over a wide area. So this paper is in review right now. It's come back with pretty good reviews. So we imagine it'll be accepted soon. Look for the Water Sense project in the EU. They're our partners for this. Okay, yes. This did not turn out the way I expected. Okay, sorry about that. I also will work on 3D geophysical inversions, where in this case, the parameters may be, say, the number and layers of rock that you have, the densities or rock properties you have within a 3D volume. The parameterization specifies those as 3D rock fields. I'm not sure why but anyway, skipping to the end of that animation. The forward models might include, for the sensors that you use to determine, things like rock densities, magnetic properties, and so on. You might be able to just drill in the ground directly, and you'll have constraints from that. You might have gravity and magnetic measurements at the surface, and you'll need forward models that give you all of those things, and that gets into some partial differential equations that you have to solve in order to do this properly with some sensors. It can be quite complex. So I worked for a while with a particular geophysical engine developed by Data61 that was meant for geothermal exploration. It was a layered geology. You were able to move the layers up and down, change their shape slightly, determine the rock properties within each layer, including their rock density and magnetism, but also temperature. So if you're looking for granite above 270 Celsius, for example, then you can find it several kilometers down and be able to actually sink your drill hole there and make sure that you've hit something good. So here's an example where you have a deterministic inversion that was done by an expert on the right, and you have a probabilistic inversion on the left where the color is related to probability density of finding granite at that depth at 3.5 kilometers down. So mostly it matches up with the deterministic inversion, but you see this bridge of rock where it actually, you might want to target that area with further data. So that then gets into the ability to say, how much is it worth to us if that intersects with other things like, well, we can't actually drill in the other places because it's on somebody's land. But if we can drill in that place, then it might be worth something to us, then it might be worth finding out what's going on there. So you can actually use that to suggest further data that you would take in order to constrain the model better. I talk a bit about the proposals that I look at, and this very last thing is a project that I'm working on now, which is trying to actually build a robot geologist. So I talked about the geophysics there and talked about sort of a parameterized model for the 3D volume and the shape of rocks in that volume. But that can be completely flexible in principle. That in fact, in geophysics generally, you just consider it as an imaging problem, and the parameters will just be the 3D field, where you're actually just inferring the rock properties in each of a bunch of voxels. And so you end up with million-dimensional problems, which are often linear, but not always. So here you've got I'm working on ways of doing inference actually over histories, where you have a forward model for the geology as well as for the geophysics sensors. So here's a situation where you might have rock layers that are laid down over time. Then you might have a tectonic event like a fault. And you might have another fault that intersects with that fault. And so you have, you build up a more complex distribution of rock properties and different geometries for geological units over time. And you can use that to go backwards and infer what was the story of how this rock formation came to be. That turns out to be harder than I thought. I took something off the shelf to try to do this, and it turned out to be a bad idea. Because if you don't take into account the projection of that geology forward model onto the grid that you use to calculate geophysics, you end up getting horrible discontinuous posteriors. And so that shows you need to actually sometimes open the box and look inside the model to see how it's being done. You can't just try to sample it with something with PyMC3 or something off the shelf. So I managed to find a way of fixing that problem by allowing for partial voxel membership in different units, which is something to be, geophysics doesn't care what the units are, but geology does. And so when you do this kind of thing, that's something you need to take into account. So anyway, that's the somewhat accelerated version of my talk. I guess the concluding thoughts I'd leave you with are that astronomy prepares you for some really cool stuff. Your skills may transfer much more directly than you think. Big data is not the only story. There are different clientele out there that may have different needs from the usual people that that will try to hire you from the boot camps. We need better decision tools for tackling environmental problems. We need to get industry and government partners working together on these problems. DARE is set up to provide those tools. And so you can maybe someday be part of all this. And if you'd like to talk more about any of this, then please find me. Thanks.
Thank you, Dr. Scalzo. We appreciate that interesting presentation about all the experiences that you've had and your journey going from academia to somewhat still academia and focusing on uncertainties and model constraints. As we all know, model constraint can be very tricky, but it's very, very important to scientific inferences. So right now we'll move on to the question and answer portion of the discussion. We do have a few prepared questions, and after we ask a few of these, we'll go to the audience questions. So I'll go first. We spoke earlier, so you said that you're from the US. I did notice that you earned your bachelor's, master's, and PhD degrees from the United States of America, but you went to Australia. So what was your main motivation to go across the Pacific down under to Australia? Was it mostly career focused, or was it a lifestyle change, a different experience living in a different country? What motivated you to go to Australia?
Well, yeah, honestly, is having a job, and that sounds a little stark, but it's kind of, but the academic job market is a global job market, and so I was also, I guess, struggling a bit at the time, and was quite close to doing something else. But I mentioned earlier that I spent a fair amount of my time working on software pipelines, and it turned out that that was exactly what my employer, Brian Schmidt, needed. And I'd heard, as I said, good things about Brian. It seemed like a good chance it did seem like a good chance to experience something else too, to move to a different part of the world and live there for a little while. So as I said, working with Brian was great, and I would absolutely do that again. Living in Australia was also great, and it turns out that I ended up staying and finding a lot of opportunities here that I might not have found elsewhere. The chance to we would say, I guess, be a big fish in a small pond is the way that Brian put it when he was talking to me earlier on when I was first taking the job. And so it does give you opportunities to lead things and experience things, and so I'm pleased to have had that opportunity.
Thanks, Richard. I was also going to ask you a little bit about your experience on, I guess, that transition from academia into, I guess, this more consulting role. And I think you went over quite a bit of that. But is there anything in particular that you found most helpful or biggest challenge to kind of overcome of leaving academia?
Well, honestly, I feel kind of a fraud that way because I'm still an academic. It's still like I'm still an academic. I'm still publishing papers. I'm still sometimes publishing astronomy papers. So, have I really left? I'm not sure, but I have rebranded. And the point here is that, and I have rebranded, and I've rebranded in order to give myself more opportunities, I guess. And that was the part of the motivation that I did that. Probably the hardest part was deciding that was what I wanted to do. And so when I went into my interview, I remember calling up and saying, so data science center, I'm thinking of applying. And it's like, I've got a degree in physics. And the director, Hugh Durrett-White, was like, you got a degree in physics. Go ahead and apply. So I applied and I got an interview. And then I went into the interview and he spent the first 15 minutes of the interview trying to convince me that what he was doing was cool. And so I'm like, aren't you going to ask me about my skills? I mean, and there was some talk about that. And I did have to discuss sort of what I had done and why it fit into what he had done. And I justified it by saying I was doing data science with astronomical data. But I think he was concerned about that. And that's also a concern if you try to go elsewhere as well. I think that, do you really want to be doing this? And then after that, we're smart people, we can learn things quickly. That's one of the real benefits of being a physics major or an astronomer. And so you can pick things up and you'll have a perspective on it that other people won't have. So that part, although difficult and, continually learning new things, I think the hardest part was just deciding to do that in the first place.
Sounds like you've got the best of both worlds anyway.
So a follow-up question to what you just said. You said rebranding, you were unsure or had a difficult time making that decision. Why so?
Well, it's just, you go into astronomy thinking, I'm here to solve the secrets of the universe, right? And that's an enormous draw. And so, you have this, it's very easy to get trapped into a mindset, I think, where everything outside of this ivory tower is basically Dilbert. And so it's easy to feel like that's the thing is that if you've got that mentality, then that ends up being the only thing that you can imagine doing, and it becomes linked to your identity in ways that I think can be unhealthy. I think that's it's becoming less of an issue. I think that new students coming in these days are sort of aware that jobs in academia are scarce, and I may have to retrain and do something else. And so you can certainly enjoy doing astronomy, and it may end up being what you end up, what you do in the future, and that's great. But that keeping a broader mind and sort of seeing what other things are out there, thinking broadly about the kinds of things you could do, and also keeping in mind, the kinds of things, thinking deeply as well about the kinds of things you want to do. What are your values? What do you really get out of, what you're doing now that maybe could be met elsewhere? Can help you think about the way to accomplish if you end up making a transition, figuring out where you want to go and what you want to do. So overcoming that mental barrier was something I found really difficult, I guess. It took me a long time to do it. That said, I haven't moved that far from where I am, but at least I can imagine, moving to some other completely different sector. But I know now that, data tools are my tools. That's what I have to offer. But the kinds of problems I want to be working on are environmental problems. And so if I move to do, something else again after this, it probably will be, some kind of environmental consultancy or independent data science consulting for environmental clients or something like that.
That's true. I have a few colleagues that have not pursued the career of typical astrophysical researcher, and they have similar hesitancy, like you mentioned. So we have a question from the registration form, which is actually pretty interesting. The question reads, what fraction of any research effort should be devoted to quantifying and managing uncertainties? Because I'm sure you don't want to spend all your time working on uncertainties, actually thinking about the relevance of the scientific result, right?
Yeah, well, to first order, it depends on, it's a very problem dependent thing, right? And the way that you deal with your uncertainties are problem dependent things. And I would say, spend effort in proportion to the degree to which, an uncertain result actually affects your qualitative answers. And that, if something is, if something is 1.4 versus 1.45 in, say, solar masses for a supernova, that probably doesn't make that much difference, right? But the 1.0 versus 1.4 is a big difference. It makes a difference, at least for the supernova problem, it makes a difference between two different kinds of, completely different kinds of explosions. So understanding how well you've constrained the thing is important to understanding the confidence with which you can say that's, a different result. And so it does depend on, I think it depends on your field, and the way you do it is going to depend on your field as well. But I'd say that's the really important thing, is that how much is this, to what degree is that going to change your conclusions? And you also, there will be different sources of uncertainty as well, but you may decide after looking at them, okay, this one's subdominant. And so you don't, if something really is subdominant, then you don't want to bother, simulating it. But if it's big and that accounts for most of your variance, then, definitely consider that.
Cool, thanks, Richard. We'll go through some of the questions that are popping up in the chat as well. So we've been asked to say MCMC is very time consuming. Obviously, you've got millions of iterations that you're going to be going through. How do we go about it for complex geological or geophysical models where forward calculation is also very time consuming itself?
Yeah. So that's a good question. You don't always need millions of iterations. Actually, it depends on the dimensionality of your problem, and in particular, it also depends on how good your proposal is. So this is something I didn't necessarily get a whole lot of time to deal with directly, but the idea, as I've said, is that I think show a slide with it where you have two different kinds of proposals, one of which didn't move at all, and the other of which did a great job at sampling the distribution that I was looking at. So that's the core of our research. That's one part of the research that's really important. Calculating this, making the geological or geophysical forward calculations faster is also important. In this case, the reason why I developed the tools I have for the kinematic models, where I've sort of got partial voxelizations of things, is because a voxelized representation is fast to calculate. And for things like gravity that are linear, you just cache a big matrix. And then, you don't have to, so then if you want to do your forward calculation, you just multiply by that matrix over and over again. So we can do fast linear algebra. That's something that we know how to do quickly, as opposed to doing integrals, which can be, frustrating and time consuming. So yeah, that's, so you do it by, so you make this tractable by paying attention to the proposal, and paying attention to the forward calculation as well. There are ways of, there are techniques where you can use emulators you can use actually a machine learning model to approximate the posterior itself, or to approximate the action of the forward model. So you might have say a neural net learn, you might generate a bunch of forward models, train a neural net on that, and then use that for your MCMC. Or you might say use different forward model calculations to learn about the posterior, but then have an approximation of that posterior that you're building up through some flexible function. And then that ends up being what you sample, 9 times out of 10 instead of the original forward model. So you can cut down on your forward model evaluations while still getting a good handle on the posterior. So this kind of thing is used in climate science, for example, where you have really complex models, but you need to have lots of forward model evaluations, but you actually can't afford it because they're very expensive models. So that's another way. So there are multiple different ways that you can get a handle on that.
Okay, so we have another question from the audience.
Mm-hmm.
Do you also manage to include indigenous knowledge in developing environmental solutions? So that's an interesting question.
It is a really interesting question, and I think it's one that's really important, and it's one that we're behind on. And in particular, I think that there's the indigenous knowledge of the actual area, and that come into that I've thought a bit about yeah, the fact that that often comes into conflict with ways that other people will be using the land, and there's a lot of discussion about native title as well, and how indigenous people will benefit from what's being done on their land, from which sovereignty was never ceded. So that's an enormous issue. Other people are farther along that road, I think, than we are, and we could definitely. I think there's also this, I don't want to fall into this sense of arrogance as well, saying, well, just let's calculate everything, right? And that'll give us the answer. And we may end up just rediscovering things that have been done for a while. So we had a project on bushfires where we looked at that, and we looked at the data that were coming in from like remote sensing data, and data on the way that the land was being used and so on. They might have been time snapshots. In the end, I think we just sort of threw up our hands and said, we don't know how to model this problem. But at the same time, in the news, in the Guardian, we saw a lot of articles about, like, this kind of controlled burn that you do is not the way that indigenous people would do it, and so it's and not for the same reasons, and so on. So there is. It is an ongoing battle. So science definitely needs to be decolonized. We need to think about decolonizing our work when we move forward. I'm hoping that if we, and I would like to see, it would be good if we could find ways of I think, recruiting indigenous people to our center as well. We need to think about improving that engagement, I would say, and that hopefully we can then start incorporating that, more of that knowledge into, if we incorporated indigenous knowledge into our priors, for example, then I think we could get something of the best of both worlds, where we can now have this expert knowledge that helps us nail down things, including the data that we can take with more modern sensors.
That'd be a really interesting kind of concept of trying to.
That's something that I would like. Yeah, that's something that I would like to do, but I have to own up that we are not doing that at the level that we really ought to be doing it at.
Ellie, I wanted to ask a quick follow-up question since you brought that up. Yeah, go for it. I've never lived in Australia. I haven't even been there yet. But how many, on average, indigenous folks of the lands of Australia participate in astronomical research at your institution?
That's a good question, and I say, at least in my experience, I think that they're quite rare. But I know that they're out there, and I follow some of them on Twitter. So it's definitely. I mean, I think Australian indigenous Australians are probably a couple % of the population at this point. So it's not, but they're still not represented at the level that they should be in astronomy. So that's another thing that we'd like to see, I'm sure, improve. But we need but I mean, it's easy to say that sort of thing, and it's another thing to have a plan to do it.
It's very true.
But yeah, they do exist. They do exist, and they are out there. And I'm pleased to see them in my feed from time to time.
There's some cool stuff they do with planetary science as well. That we've got some colleagues in that area, which is really exciting. So I have a question. It's a bit of a change of subject. It's a bit of an unusual question. I'm not quite sure if this is the best way to ask it, but generally tend to find that you get different standards of across fields for what uncertainty is and what's acceptable levels, and how to actually address them. And so, for example, from physics to astronomy to earth sciences. And I guess I don't know if there's a problem in that, but also I think my main question is about, for journals that are covering a really broad range of fields, especially high impact ones like science and nature, are these different standards of uncertainty across the different fields, are they kind of affecting how the publication or the quality, is there a quality control from the publication side for these different science outcomes when you've got such a broad audience? And in particular, I guess, how is this maybe even affecting the general public's view of good science, I guess?
Yeah, no, it's difficult because as I think I might have touched on, quantification of uncertainty is a different points in different fields, and a lot of I think everybody thinks about uncertainty at some level, but the tools that they use are field dependent, and it may depend on the ways that uncertainty is tied up with their ways of thinking about science. So geology, for example, is very about narratives, and so they may think about uncertainty by generating a few ensembles of models, but they won't necessarily do that according to a probability distribution, because they won't necessarily have quantified that in that way. But they have thought about it, right? And it's tough to apply a uniform standard of uncertainty quantification across the entirety of science when they have such different ways of thinking about things. Biology is another example.
Different data formats and.
Yeah, well, not even just data formats, but like, how do they tell a scientific story, right? And do they do it with math, or do they do it in some other way? So biologists, a lot of the biologists I've worked with will generally not touch linear algebra with the 10-foot pole, but they're very clever at coming up with ways to. They're very clever at coming up with ways to design an experiment in such a way that the answer will be immediately apparent just by looking at a blot, for example. And that's something that I'd have to have math to design experiments. So that sort of thing is important. It's hard to hold everyone to the same standard. I don't know about, my take is that I would be surprised if this made the fact of having different science standards of uncertainty made a big difference to the public's interpretation, because you're almost never saying, oh, this is a 5 sigma result, and expecting the public that to mean something to the public, right? I think it's more along the lines of, have you told a coherent story about what's going on? If you told me a coherent story and you're convinced that you found something new, then that's probably, I would think that again, I would defer, I guess, to the science communicators on this, because they'll know, and they'll have actually gotten a lot of questions. But my impression, at least from what outreach I've done, is it's mostly about telling a coherent story and being able to say, by the standards of your fields, have you found something new, or do you have confidence in your own results? The places, I guess, that you might worry most about public confidence in science, I think also are not really related to uncertainty quantification. It's more situations where the existence of uncertainty is being used in bad faith to undermine the confidence in science. So, vaccine hesitancy and climate science are among the most prominent of those, probably the worst of those. But I don't think anyone is, and it's, and it's not that climate science doesn't have error bars, but that they do. They have uncertainties, and they'll say there's a range of uncertainties, but all the scenarios going forward are very urgent. So that the qualitative results doesn't actually, the qualitative results may hinge a bit on that uncertainty, but the decision we are making on that front should not. So that's a case where that is an uphill battle, and it's. But I don't think it depends on the details of how things are quantified in climate science versus how they're quantified in astrophysics or geology, for example.
Quick follow-up question. Have you ever encountered falsification of uncertainties or error bars?
Never. Falsification, no.
That's good to hear.
Falsification, that's I think falsification in science is very rare. And when it happens, it really makes headlines. And we saw, I think it's more common to rush to results. I'm thinking of the BICEP2 cosmic microwave background press conferences a few years back, where where they only later found out that their signal was due to dust instead of gravity waves. And so it's kind of like, so it's that sort of thing you do have to watch out for, but that sort of thing should be caught by the review process. Or, some things, sometimes the reviewers can miss things too. They're only human. But I think the actual rate of falsification is very low. So.
Well, thank you very much, Richard. I think we've pretty much just about run out of time there. So I'd like to thank you again for your great talk, and thank all the people here who have been attending live, and for those of you that are going to be watching it later on YouTube. And not to forget that on Thursday, the 27th of May, at the same time, we'll be listening to Dr. Natasha Hurley-Walker from Curtin University on exploring the universe without costing the Earth. So looking forward to seeing you all then. So thank you very much, everyone, and have a good day or have a good night.
Thanks, everyone. Thanks for having me.